Hello everyone, and welcome to Calculus Lesson 1-8. We're talking about continuity today. So the first question that everybody asks me is, what is continuity? Now, a function is continuous at a number a if the limit as x approaches a, f of x equals f of a. So basically, when we were evaluating limits using substitution, where we just took this a number and put it into the function, we were using the fact that the function is continuous at that number. Okay, if a function is continuous, then this will work all the time. So it's important to be able to determine if something's continuous. So we have these three conditions that need to be met. Okay, and this is implied by this definition of continuous. Okay, it means that f of a, when you evaluate, it actually is defined, meaning that a is in the domain of the function. And that's why we spend so much time talking about finding domains. The second thing that's implied is that this limit actually does exist. Okay, so it's not a does not exist limit. And finally, that limit that does exist is actually equal to f of a. So it's saying that this is defined, this exists, and these two things are actually equal. That's what continuity is. That's what's implied by the fact that a function is continuous, meaning that there are no breaks or gaps or holes or jumps and things like that in it. We're going to take a look at types of discontinuity in just a minute. Okay, so we're going to use these three implications to determine places of discontinuity on a graph. In example 1, it says the picture shows the graph of a function f. At which numbers is f discontinuous and why? Okay, so pause the video, see if you can write those down, and then press play to check your answers. Okay, so it's discontinuous at x equals 1, 3, and 5. Those are the three places that it's discontinuous. And this is why. At x equals 1, this condition is not met. F of a is actually not defined because f of 1 has an open circle and there is no filled in circle anywhere on the 1 line. So that is wrong. At x equals 3, the limit as x approaches a does not exist, because as it approaches it from the negative side, we're going down here to a negative number. As it approaches 3 from the positive side, we're going to a positive number. It doesn't meet there. So that limit does not exist. At x equals 5, the limit exists, but guess what? That limit does not actually equal the evaluation for f of 5. Okay, so at each of these points, we either have a hole in the graph, a jump in the graph, or this is what we call a removable discontinuity. So let's take a look at more examples where we need to find values of discontinuity. In example 2, we need to determine where each of the functions is discontinuous. So remember, check the domains, see if something's not allowed in a domain, because that's going to be a place of discontinuity. Check the graph, see if something's happening, if there's a break or a jump or a hole somewhere. Okay, so see if you can determine places where each of these is discontinuous, and then press play and check all of your answers. In part A, it's discontinuous at x equals 2, because if I put in a 2 here, I'm going to be dividing by 0, which is not allowed. So this function is undefined at this point. So I can't do f of 2 here. In part B, it's discontinuous at 0 because if I put in a 0 here, it's undefined. If I put a 0 in here, I get 1. So it's going to jump to the value of 1, and leading up to 1 from the negative side and the positive side, this will not fill the hole there. At 1, it's going to an infinite discontinuity. Okay, so at 0, it's going to have a problem. For part C, it's discontinuous again at 2 because, again, it's jumping values. Okay, as it approaches 2, Again, you'll notice that there's like an infinite discontinuity. And then at 2, we're getting just the value of 1. So another discontinuity there because it's piecewise. Now, not all piecewise functions are discontinuous, though, so be careful about that. Don't just assume. You have to check. In part D, okay, this is the greatest integer function. This is discontinuous at all integer values because it's where it steps, where it jumps to the next value. So at all integer values, at 1, at 2, at 3, at 4, or 0, -1, -2, -3, all of those are discontinuities in this graph. So let's take a look at the different types of discontinuity. Okay, a jump discontinuity is where the function is continuous all the way up to a point, and then suddenly it's going to jump to another value and then be continuous from there on. This is a jump discontinuity because it jumps from here up to here. A removable discontinuity is where there's a hole right here, and then it's just evaluated at a different value right there. That's removable. And finally, an infinite discontinuity is where it's going down to -infinity or up to +infinity at a certain value. Okay, so that is an infinite discontinuity. So in your homework, you're going to be asked to like name them from a graph. So make sure you're aware of what these are. They kind of make sense when you think about what they are. Like removable means a spot has been removed, a jump means it jumps from one value to the next, and infinite means it's going on to infinity. Now let's talk about continuity from the left side or the right side. So a function is continuous from the right at a number if the limit from the right side of that is actually equal to evaluating for that value. Okay, so that means that if I have like a removable discontinuity or a jump discontinuity, it might be continuous from the right or the left. So let me bring up that other graph that we had. This one is actually continuous from the left side because as I go to the left, if I evaluate it for f of a, it's going to work. So from the left side here, it is continuous all the way up to this point. But it's not generally continuous all the time. It's just from the left side, it would be considered continuous. Okay, or from the right side if it had a filled in circle on that right side. Okay, so let's take a look at an example where we have to determine if something is continuous from the left or continuous from the right. In example 3, they're giving us the greatest integer function again, and they want to know if it can be said to be continuous from the left or the right, and we need to explain our reasoning. So take a look at this graph, decide if it's left or right, and then press play to check your answer. Okay, so this function is continuous from the right and discontinuous from the left because as I'm approaching from the right, I have a filled in circle at +3 or a filled in circle at +2. So as I'm going from right to left, I'm going to be approaching a filled in circle. So that means it's continuous from the right. If I'm going from the left side this way, I'm approaching an open circle. So it's discontinuous from the left because it's approaching an open circle from the left side. Okay, so it's continuous from the right, not from the left. Now let's take a look at continuity within an interval. A function is continuous on an interval if it's continuous inside that interval for every number in there. Now, for the endpoints of the interval, it does matter if they're including those endpoints or not. And you have to check the notation of what they gave you for the interval. So in my picture here, if my interval was from A to B, not including A to B, then I could say that this is continuous, even though this endpoint here is not included and this endpoint here is not included, because everything in between A and B is included. Now, if they had square brackets on A and B, then I would say it's not continuous because you can't evaluate for A and you can't evaluate for B. So just watch out for that notation. But let's take a look at an example and it might become a little more clear. Now, a lot of times instead of looking at a graph, we look at just a function and we try to evaluate that function for a value. So take a look at the algebra I'm about to do. In example 4, it asks us to show that the function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval -1 to 1. Okay, so what I'm going to do is I'm going to use the limit laws, and this is my little note to you. Use the limit laws to simplify and then see if the limit as x approaches a is equal to evaluating for f of a. So that's your step 1. Step 2 is to actually take -1 and put it in, and take 1 and put it in, and see if it can actually be evaluated for those, because they're actually included in our interval. So go ahead and do that, and then press play to check your answer. So what I did first is I checked my limits as it's approaching -1 from the positive side, because I'm including the ones that are more than -1 and going down to -1. I found out that you can evaluate for -1 and that limit would equal it. Then I checked approaching 1 from the negative side because the values are less than it. And I saw that you can evaluate for 1, so I did, and the limit would equal that. So you always want to check those endpoints. And then I used my limit laws. So you'll notice that first I did the sum law and the square root law and the difference law. So it was the limit as x approaches a of 1 minus the square root of the limit as x approaches a of 1 minus the limit as x approaches a of x squared. And then what I did is I just simplified this. This says you just get 1. This just gets 1, and it's minus, this would be a squared. Okay, so this is what I got as my result. Now, if I put in an a into this function, I do get this result. These are equal, so it is continuous on that interval. And I know it kind of seems like circular reasoning, but I just needed to give a good reason as to why this limit is actually equal to just evaluating for f of a. And that's what I did. So it is continuous because not only can I evaluate for -1 and 1, but I can also use my limit laws to show that my limit is equal to evaluating for a. Okay, so that's it for this video. Don't forget to watch the next video where we talk about combinations of functions and some other theorems that we need to use for continuity.